Hi guys, this is George from Hardwire Electronics. I hope that you're doing well today. In this video I'd like to take a closer look at the CAN bus. We found that a number of our customers using our PDMs are perhaps a little bit confused or overwhelmed when it comes to understanding the CAN bus. That's both when physically wiring the CAN bus and when configuring devices to use the CAN bus to send and receive data. Now this is quite understandable as the CAN bus is not exactly a straightforward topic to understand. So there's already a number of learning resources out there on the internet which go into a lot more detail than what I will here in this video. But I'd like to make this video as a base guide for our own customers who want to learn and understand the CAN bus in a little bit more detail. And it's a video that I can hopefully point you to when you have questions or become stuck and you need a little bit more explanation about what's going on. There are a lot of seemingly arbitrary rules which we hear about when wiring up the CAN bus, such as the use of termination resistors of a certain value, the need to use twisted pair wires, the need to keep stub lengths to a minimum, and much more. And I'd like to demystify some of these rules and try to put a little bit of solid theory behind why those rules exist. So this video will likely be quite long, so we'll probably split the video up into two. So this will be the first video. I hope you guys enjoy it, and if you have any other questions or need further clarification on any points, then just let me know via email and I'll make sure to help you with your needs. Please enjoy. We'll start by going over some of the physical properties of the CAN bus before then moving on to the actual CAN bus protocol itself, and then after that we'll look at some real world examples and I'll show you how to receive data on the Hardwire PDM which has been sent from another ECU. Now, as many of you will be aware, the CAN bus is used extensively in the automotive industry, and there's a good reason for it. It allows multiple devices to reliably communicate with each other at a reasonably high data rate and for a reasonably low cost. And this is ultimately why we see the CAN bus used as a primary method for sending data between different devices in a vehicle. So as we'll get into in this video, the CAN bus has a number of clever features, both at the hardware and the software level, which make it an incredibly resilient and reliable method for sending data. So the CAN bus uses two wires for sending data. It uses the CAN high and the CAN low wire. And I'm just going to draw this now for you. So generally, you'll find that the yellow wire we say is the CAN high, and the green wire, which I'll just draw now, is the CAN low. So generally they're the colours that you'll find in industry, green and yellow. So here's the CAN bus. I've drawn them as wiggly lines here, and that's to kind of signal that the wires are twisted in a pair. And what you'll find is when you wire in the CAN bus, you want this distance to be about 1 inch. So 1 twist per inch is a pretty reasonable target to aim for. It's not really too critical. You can get away definitely with more twists, and you can get away with less twists. But around that level is absolutely fine. Now, the other thing you'll see is that at the end of the CAN bus, you're actually going to have two what we call termination resistors. So I'll draw them in here, and they will connect at either end of the CAN bus to the CAN high and the CAN low wires, and they must go at the end of the CAN bus. Now the value of these resistors is 120 ohms each. So when you come to a CAN bus, you can check if the termination resistance is correct, because you can actually put a multimeter, on the CAN high and CAN low, and it should read 60 ohms approximately, which is the parallel combination of two 120 ohm resistors. On the CAN bus, then you would have your nodes attached to the CAN bus as follows. So you might have one coming off over here, one coming off over here, and this might be your PDM, and this might be an ECU, and you might have other devices on the CAN bus as well. But this is generally the kind of setup that you'll see. Now it's important, we'll get back to this in a moment, but it's important that the stub length here, that's the distance from the CAN node to the main CAN bus itself, is less than 30 centimeters. So let's just take a moment to actually consider why we want to use 2 wires for the CAN bus. Why can't we just use a single wire between devices? And you put a voltage on the wire, the other device detects it, and you can send data in that manner. Well, there's a good reason for this. And if I just draw, as an example, if I just draw a graph. So let's say here we have time and voltage on here. And let's say that we're sending a signal over a single wire. And here this might be 0 volts, and this might be 5 volts. And you're going to get your data bits, so we'll have a 0, and then we might transmit a 1, then a 0, maybe another 1 here, and so forth. You can transmit bits like this. Why can't we just use a single wire to transmit our data bits? Well, there are a number of good reasons why we use 2 wires on the CAN bus, and I'll get over more of them in a moment. But one of the main reasons why we use 2 wires and not 1 is that 2 wires helps us in terms of our resilience to electrical interference and noise. So let's just look at this is for a single wire setup, and if we get, say, a voltage spike here, like this, and we might have a voltage spike here, this can cause us big issues. And why is that? So at the receiving end of this transmitted data, we're going to have a receiver which is looking at the voltage on the line, and the voltage on the line will determine whether it thinks a 1 has been transmitted or a 0 has been transmitted. So here, obviously, this would be a 1, this would be a 0 because it's a low voltage, this would be a 1 because it's a high voltage. But we also have these 2 voltage spikes here which have been caused by electrical noise. And there's no way for the receiver to know whether this is, just a piece of noise or whether it's actually a 1 data bit. So that might be registered as a 1 momentarily, and this might be registered as a 1. And now instead of what it should be, which is 0, 1, 0, 1, 0, we now have 1, 1, 0, 1, 1, and that's obviously going to cause us errors in our communication. So that's actually one of the reasons why we mostly don't use a single wire for transmitting data. Now there are ways around this. We can increase what's called the signal to noise ratio, so we can actually increase the level of the on bit of the 1. So let's say we increase this up to 12 volts, and now at the receiving end, because we are expecting a larger signal, a 12 volts for a digital one, these voltage spikes here won't cause us any problem. They will still be registered as a 0. So that's one method you can use to get around this problem, but this means that the transmitter and the receiver now, instead of only having to deal with a 5 volt signal, have to be able to work with a 12 volt signal, and this can cause its own problems. So the question then is, how does 2 wires, a twisted pair, help with this problem that we've got here? And so we'll go over that now. Let's draw another graph. I'm sorry for all the graphs, but it's quite important to be able to realise what's going on. So we'll have another graph here. And now let's show how the digital bits are sent using the CAN high and the CAN low signals. So the CAN low will go like this, and I'll explain what's going on in just a second. And the CAN high will go like this. And importantly, you will see that they are a mirror opposite. So we have the CAN high and the CAN low. And the voltages that we're dealing with here, this central voltage here will be approximately 2.5 volts. Up here this might be 3.5 volts. And this lower voltage here will be approximately 1.5 volts. And then we have 0 volts here as well. And this again is time. So now instead of a 0 bit being low and a a 1 being high, we're now working on the difference between the high and the low signal. And perhaps counterintuitively, this section here would be considered a digital 1. This would be considered a digital 0, a 1, 0, and then 1s here as well. So how does this help us with our noise issue? Well, let's have a see. The first thing to note is that if we have a noise source over here, and that's sending out electrical noise through the air, and that's going to be coupled onto the CAN high and CAN low wires. And because the distance between this noise source and the CAN high wire and the noise source and the CAN low wire is the same, what we'll see is that the voltage which is induced onto the CAN high and CAN low lines is equal for both. So we have a voltage spike here on our CAN high, and we'll have an equal voltage spike on our CAN low. And on here, on our CAN low, we'll have one, and on our CAN high, that will be exactly the same. And again, here we'll have another one, and here we'll have another one. Now, how does this help? We still have voltage spikes on our CAN high and CAN low. Now, this is where a technique called differential signaling comes into play. So the way that differential signaling works is that at the receiver, we detect a 0 and a 1 based on the difference between the CAN high and the CAN low signal. So working on only the difference, we can now see that if we draw another graph here underneath, and this is going to be what the receiver makes of this CAN high and CAN low voltage signal. So it's going to subtract the CAN high voltage from the CAN low voltage, and the difference between the two is what's going to give us our bits. So if we manually look at the difference in voltage at a couple of different points, just to go through this together, we can look at this point, here, 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 and here. So at this point, CAN high minus CAN low is 2.5 volts minus 2.5, that's going to be 0 volts. At this point here, we have 3.5 minus 1.5, so that's going to be 2. Okay, and here if we subtract CAN high from CAN low, this, let's say that this is 4 volts, and let's say that this is 2 volts. Again, CAN high minus CAN low, that's going to be 2. And here, let's say that this is 3 volts, so that's going to be 3 minus 3, that's going to be 0. And here, 4 minus 2, that's going to be 2. And here, 2.5 minus 2.5, that's going to be 0. So now, if we draw the voltage difference that we've got here on this bottom graph, what we'll see is we've got, I'll just draw it in white, we've got a 0, and then here it goes up to 2, goes across, comes back down to 0, and across, up to 2, back down to 0, and then we've got zeros here, and this is going to be 2 volts, this is going to be 0 volts. So now you can see that simply by subtracting the CAN high voltage from the CAN low voltage, we have removed the voltage spikes that have been induced onto both signals. Now this is incredibly useful. It means that we have basically removed the noise for free. And this is an incredibly powerful technique. It's used all over in telephone wires, in Ethernet cables, in CAN bus, as you see. It's used all over the place because of this fact. By subtracting one from the other, you remove the common mode signal, which in this case, the voltage spikes that we see are common to both signals, so that's removed. All we're left with is the difference between the two signals. Okay, so just to demonstrate this effect a little bit more clearly, I've actually set up a CAN bus in real life, and I've got an oscilloscope probe on both the CAN high and the CAN low wires. At the minute the scope's running, so you can't see too much, but if I just freeze frame this for a second, what you can see, I purposely made it so that there's a little bit of noise which has been induced onto the CAN high and the CAN low lines. And what I've also set up on the oscilloscope is a maths channel, which is actually taking the difference between the CAN high and the CAN low signal. And even though you can see that the yellow and the green trace is quite noisy and it doesn't look particularly nice, you can see that the purple trace, which is the difference between the CAN high and the CAN low, is a lovely noise-free digital signal without any artifacts. This is essentially what's happening inside each CAN controller. It's taking the difference between the CAN high and the CAN low, and that's actually subtracting away all of the noise, leaving you with the original signal, which is what we want. So that's one reason why we use a twisted pair wire to transmit our data instead of just a single wire. Now, we've seen how using a twisted pair helps us be more resilient to external electrical interference, but there are a couple more benefits as well to using a twisted pair wire to send our data. So any wire that has data being sent on it like this will produce its own electrical noise, which is transmitted into the air, which could affect other devices in the vicinity. So the CAN high here, that will be transmitting out, the CAN low will be transmitting out, but importantly, because the CAN high and the CAN low wires change in opposite directions, so when the CAN high wire goes up in voltage, the CAN low goes down in voltage, and vice versa. When the CAN low goes up in voltage, the CAN high is coming down in voltage. What we see is that the electromagnetic wave being transmitted from the CAN high signal is perfectly cancelled by the electromagnetic waves being transmitted from the CAN low signal. And the result is that to an external observer over here, the CAN bus is generating no electrical noise. So this is incredibly useful as well. It means that we can bundle lots of these together. They're not going to interfere with each other, and it means that we don't really need to use a grounded shield on the CAN bus either. So that's another reason why using a differential pair is extremely useful. Okay, so the next question that you might have is, why do we need to use these two resistors at the end of the CAN bus? So there are a few reasons why we need to use these resistors at the end of the CAN bus. To explain the first reason, we need to understand how the CAN bus transmitters actually send data, how they write ones and zeros onto the bus. Now, CAN bus transmitters are called open collector, and that means that they can only drive the bus in one direction. They can only actively write a zero onto the bus. A 1 is the default state that the bus goes into when nothing is trying to write onto the bus. So let me try and explain this a little bit better. So on the CAN bus, a digital 1 is considered to be recessive, and a digital 0 is considered to be dominant. Now, what does this mean? Well, a 1 is the recessive state of the bus. When no CAN transceivers are writing onto the bus, this is the state that the bus will take. The CAN high and CAN low will come back to 2.5 volts. If you want a 0 on the bus, that's when the CAN transceiver will write a 0. So effectively what this means is that if a CAN transceiver wants to transmit 10101, it has to go, okay, here we're not going to do anything, now we're going to write a 0, and now we're going to let go of the bus and let it come back to 1. Now we're going to write a 0, and now we're going to let go of the bus and go back to 1. This is an important part of the CAN bus, which we'll get onto later when it comes to bus arbitration, but this is one of the reasons why we need to use these resistors at the end of the CAN bus. When the CAN transceiver is not writing onto the bus, we want the bus to come back to this recessive state. And these resistors help pull the CAN high and CAN low lines back together to 2.5 volts. So that's one reason why we use these resistors at the end of the bus. The other reason why we use these resistors is to stop what's called bus reflections. So let's say that the PDM here transmits a 0 on the CAN bus, and that is moving down the CAN bus from the PDM transceiver here. It's moving down the bus in this direction. Now when it gets to the end of the bus, we don't want that to be reflected back. And what these resistors at the end of the bus do is that they stop any reflections. So when it gets to the end, that's it, it stops. Now this is very important because if this signal reflects at the end of the bus and comes back in the opposite direction, that can cause bit errors, which ultimately results in errors in your CAN bus message. So these resistors help stop reflections at the end of the bus. And why do we use a value of 120 ohms at the end of the bus? Why not, a 1k resistor or a 500k resistor? Without getting into transmission line theory and characteristic impedances too much, effectively the reason we have a 120 ohm resistor here is because that somewhat matches the characteristic impedance of the twisted pair CAN bus wires. And that means that we don't have impedance mismatch at the end of the bus, and the signals aren't reflected backwards. So that's why the value is picked to be 120 ohms. It's not super critical. 100 ohms here would be fine. 140 ohms would probably be fine. But 120 ohms is what's written in the spec for CAN bus, and that's because it closely matches what the typical characteristic impedance of two twisted wires would be. And that again is one of the reasons why we use a twisted pair wire with a regular number of twists per inch. And that's because it keeps the characteristic impedance of this transmission line at a fairly constant level, and it helps to stop any internal reflections. So another reason why a value of 120 ohms is chosen is because it helps to control the slew rate of the signal. So as you can probably imagine, the lower this value of resistance here, the stronger the resistor is pulling the CAN high and CAN low lines together. And what that means is, on the falling edge of these signals, we get a nice sharp drop down in voltage like this. Now, if the termination resistors were something like 500k, then due to the capacitance on the CAN bus itself, instead of getting this nice sharp drop down in voltage, you get a real slow drop like this. And that's obviously not what you want. You want nice sharp transitions between your 0 and 1s. So that's why we use the resistors at the end of the CAN bus, and why the values of 120 ohms are typically used. Okay, so this also ties into the fact that we need to keep the what we call the stub length, which is the distance between the main CAN bus and the CAN bus nodes, at less than 30 centimeters in length. At the actual CAN bus node right here, there are no termination resistors, and when a signal reaches the CAN bus node, you will get reflections that come back down onto the main bus. And what you'll find is that if the stub length is kept to a minimum, when the signal comes down to the node and then is reflected back up to the CAN bus, the actual rising or falling edge which you find on the CAN bus as the data has been transmitted hasn't moved that much with respect to the reflected signal if the distance is kept really short. But if the distance is really long, then by the time the reflected signal gets back to the main CAN bus, this edge has moved along, and then you end up with artifacts in the rising and falling edge of the CAN bus bits. And this can then cause issues because the rising and falling edge of these bits might not be very clean, and then at another receiving node you could get erroneous bit flips on this transition. So that's the reason why we keep the stub length really short. And just as another point, we see a lot of people using these CAN bus hubs, and effectively this is a box, and it has it might have a connector here, a connector here, here, and here. And internally, what you'll find is that they're connected up as so, with the CAN high and CAN low lines. And people are then tempted, because it's quite convenient to have this in a central position, and then have a big stub coming off here to your PDM, another stub coming off here to your dash, another one coming off here maybe to your ECU, and maybe one here going to some other device, and then one here going to another device. Instead of a CAN bus, you've got now a star connected system. You might have your termination resistors here and maybe here, but these stub lengths are greater than 30 centimeters, so you're getting reflections back along here. This is greater than 30 centimeters, and this is greater than 30 centimeters, and it can cause all sorts of issues with signal integrity. And this is one of the leading reasons why we see people's CAN buses not working. It's because they're using these CAN bus hubs in a way which they're not intended to be used. How they're actually supposed to be used, I'll just show you now. So there's absolutely nothing wrong with using a CAN bus hub if you actually pay attention to these rules that we have up at the top. So you can have your PDM over here connected to the CAN bus, and you could have your ECU over here, and you might have your termination resistors here and here, and this is all great. This is still a CAN bus at this point, And then all you have to make sure is that the stubs coming off here are less than 30 centimeters. Like this. And as long as these distances here to the main bus are less than 30 centimeters, you'll be absolutely fine. You won't get any issues. It's when you start increasing this out over here and it's going off to the back of the car and it's coming back again, this is when you start getting problems. So that's just a little tip when it comes to using these passive CAN bus hubs. Okay, so another very common thing that you see is that the actual CAN node itself has an internal termination resistor. You'll find this on our PDM25, for example. You have your PDM here, and that actually has the resistor internal, which can be selected on or off. And if you are to use this internal CAN bus termination resistor, you need to make sure that this node is the node that's at the end of the CAN bus. There's no use in this being halfway, because you still need to make sure that the resistors are at the very end to stop reflections back and forth up and down the bus. And so there's absolutely nothing wrong with having your CAN bus like this going to another device like your ECU. There's nothing wrong with that. You know, you might have your internal resistor here, or indeed if you're not using an internal resistor, you might have to add one on the outside of the bus here as well. Ultimately, you just need to make sure that the resistors are close to, if not at the very end of, the CAN bus like this. Okay, so earlier on I just touched on the fact that it's maybe a little bit counterintuitive that this here would be a 1 and this would be a 0, and this would be a 1 and this would be a 0 and this would be a 1. You know, normally you would expect that this difference in voltage here would represent a 1 instead of a 0. There's a good reason for why this is. Why 1 is considered the recessive bit and why 0 is the dominant bit. And to get onto why that is, we'll now move on to the actual CAN protocol itself. Okay, so over here I've just inserted an image of a typical CAN bus packet. And to begin with, this can actually look pretty confusing. There's a lot of stuff going on. But I'm going to break it down into its individual parts, and hopefully by the end of this you'll understand what each bit does and why each bit is important. So the SOF, that stands for start of frame. Now, as we know, a digital 1 is the recessive state. So when no messages are being sent on the CAN bus, the voltage on the CAN high and CAN low lines will be 2.5 volts. Now, to signify the start of a frame, we actually make the CAN bus go to a dominant state. So we transmit a 0 bit. So this is start of frame. And to signify the start of a frame, we send a 0 bit. Now, the next part of the packet brings us to an interesting point when it comes to the CAN bus, and that is that each message has its own identifier. So in the CAN bus, the 11-bit identifier signals what the actual CAN message is about. It's not an address or anything like this, it's an identifier for the data bytes. And there are two types of CAN messages you can get. You can get a CAN bus message with 11 bits. So an 11-bit identifier allows up to 2048 unique IDs. Now, if you've got a large CAN bus system with lots of different types of messages being sent, you can soon get through all 2048 different CAN bus IDs. And so CAN bus introduced what's called the extended identifier, which is 29 bits long. And so a 29-bit ID allows up to 536 million different CAN bus IDs. But in this video, we're just going to focus on 11-bit identifiers. Effectively, it's exactly the same when we're working with 29-bit IDs, but in this video, I'll just stick to 11-bit IDs, so it makes it a little bit easier for us. So next we have the RTR. And the RTR is a single bit long, and that tells us if we're sending a CAN bus message with data bytes or just a CAN bus message on its own without any data bytes. So basically just the ID being sent. So the IDE is a bit that is used to tell us if we're using an 11-bit identifier or the 29-bit identifier. R0, that's not used, that's just a reserved bit. The DLC, that's the data length, so that tells us how many bytes are in the data section of the packet. So in the standard CAN bus format, you can have between 0 and 8 data bytes in a CAN packet, so that tells us how many data bytes to expect. Then we have the data bytes themselves. And then we have the CRC, which is a cyclic redundancy check. And that is just an error checking code. And that means that if we get a bit flip in our data bytes or in anywhere else, the CRC will be able to identify that we've had a bit flip. And then we can discard that message as been faulty. And then we have an acknowledgement, an end of frame, and this extra bit at the end here we don't need to worry about. So I know that was quite a quick and brief overview of the different parts of the CAN bus packet, but for us in this video we only really need to concern ourselves with the identifier, the DLC, and the data bytes themselves. The rest of the CAN packet, obviously it's useful to know what each part is, but it's not really useful for us in this video. So you might have the question, how do you schedule which CAN bus node can transmit onto the CAN bus at any one time? How does the PDM know when to transmit its message, and how does the ECU know when to transmit its message, so that we're not causing huge conflicts on the bus, we're not trying to send at the same time, and we're not causing a load of issues like that. So this comes down to what's called bus arbitration. And bus arbitration is a clever system which allows us to automatically decide whose message is going to go into the CAN bus. So let's say, for example, that we have the PDM and the ECU both trying to send a CAN bus message onto the CAN bus. And the ID of the PDM message is 0x001, and the ID of the ECU message is 0x003. So in binary, this would read out as 0, 0, 0, 0, 0, 0, 0, 0. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a 1 here. And for the ECU, that would be 0, 0, 0, 0, 1, 1. So this is the binary representation of this hexadecimal ID that we have here. So it's 11 bits long. So it's 11 bits long, and when the CAN bus message is actually sent, it's sent with the most significant bit first. So this 0 is sent first, then this 0, 0, 0, 0, 0, 0, 0, 0, 0, and then a 1 after. So let's say, for example, that both the ECU and the PDM are trying to send the CAN bus message at exactly the same time. Now what happens in that situation? So both the PDM and the ECU try to transmit their CAN frame with its ID of 1 for the PDM and 3 for the ECU. And to start with, they're going to transmit this start of frame bit. And the start of frame bit is going to be a dominant 0. So we'll write down here, they both transmit a 0. So this is going to be a 1 and this is a 0. And now that they've both transmitted the start of frame bit, they move on to the 11-bit ID. And for the PDM, it's trying to transmit a 0, and the ECU is trying to transmit a 0, so they both transmit a 0 at the same time. And at this point, neither the ECU or the PDM know that the other device is trying to transmit onto the CAN bus. All it can see is that it's writing a 0, and everything's going great. So then we have a bunch more zeros here, so I'll just write them in. It's the same for both the ECU and the PDM, so they transmit a bunch more zeros. And then we get to the 10th bit of the ID, and this is where the interesting thing happens. Because as you can see, the PDM's ID, the 10th bit, is 0, and on the ECU, it's a 1. So the PDM transmits another dominant 0, and the ECU, it tries to transmit a 1, which is the recessive bit, but instead, because the PDM is already transmitting a 0, and that's the dominant bit, a 0 is in fact transmitted instead of a 1. And at this very moment, the ECU detects that another device is transmitting on the CAN bus, and it immediately stops transmitting the rest of its message. The PDM still has no idea that there was another device trying to transmit at the same time, but the ECU knows because it tried to send a 1 and instead there was a 0 on the bus, it knows that another device is transmitting. And the interesting thing here is that the sender with the lower ID is the one that won the bus arbitration. So the PDM carries on sending its data and the ECU stops immediately. Now this is very useful because it now allows us to automatically give CAN messages with a lower ID a higher priority. If you have time critical messages that need to be sent and can't be held up, then you will give them a lower ID. And if you have something like a temperature reading which isn't time critical, then you can give it a higher ID, and that means that a CAN message with a lower ID can be sent instantly and it isn't hampered by other less time critical messages. So that's CAN bus arbitration, and that tells us why we somewhat counterintuitively have 1 as a recessive bit and 0 as a dominant bit. And it means that having a lower ID allows messages to have a higher priority. So I should also point out that each CAN node on the CAN bus is actually listening to itself. And this is an important point. It's listening to what's happening on the CAN bus at all times, even when it's transmitting out. And that allows it to immediately come off the CAN bus and stop transmitting a message when another device wins arbitration. This also brings us on to another point, which is that you need at least 2 CAN bus nodes on the CAN bus for any data to be transmitted. The act of actually sending a CAN message requires participation by at least 2 CAN nodes. And what do I mean by this? Well, as you can see, at the end of the packet we have what's called an ACK, which is an acknowledgement. And the acknowledgement is there to let the transmitting CAN bus node know that its message has been received properly. So it sends out its messages, and when it gets to the ACK bit, it leaves the bus in a recessive state, and it's up to the receiving nodes on the bus to pull the bus into a dominant state, to put a 0 onto the bus. And if the sending node doesn't detect that the bus has gone to a 0, it knows that no other devices on the CAN bus have successfully received that message. So this about wraps up everything that you need to know about the physical aspects of the CAN bus and also the protocol level of the CAN bus. So from here we'll move on to looking at some real world examples. So I want to show you how to read some real life data from the CAN bus, and in this case we're going to be sending data from a Fueltech ECU to a Hardwire PDM, and then on the Hardwire PDM we're going to look at how to read this data, how to extract the variables from the CAN packets themselves, and how to format this data so that the PDM can use it as the ECU intended.